So I'm going to give an intro to optics with that patient. Of course, we all love our patients, but we know there can be those patients. And you know what I'm talking about. So you get to the clinic. It's 8 o'clock. You barely had your coffee. You pull to the exam lane, grab the first patient. And there he is. And he says, so I've been thinking about the universe, about life. What even is light? You're dreaming of your coffee, thinking, why am I here? But fortunately, you have some references on hand. So you pull out your pocket Encyclopedia Britannica and you flip over and you say, what is light? And you pull up this doozy, 3 paragraphs. No single answer to the question, what is light? Satisfies the many contexts in which light is experienced, explored, and exploited. The physicist is interested in the physical properties of light, the artist in the aesthetic appreciation of the visual world. Through the sense of sight, light is the primary tool for perceiving the world and communicating within it. Light from the sun warms the earth, drives global patterns, and initiates the life-sustaining process of photosynthesis. On the grandest scale, light's interactions with matter have helped shape the structure of the universe. Wow, that's a lot. So you're like, I think I need something a little more succinct. So you turn over to your handy ChatGPT. What is light? Boom, and it spits this out. Light is a form of electromagnetic radiation that is visible to the human eye. Okay, that you can work with. Right? Light travels in straight lines called rays, and it can exhibit properties of both particles and waves. Okay, so now we're getting somewhere. So this is the electromagnetic spectrum. You probably saw this somewhere in grade school, I imagine. And so light, I agree with this definition, is an electromagnetic wave. And light that we perceive is in this visible spectrum. It falls between roughly 400 nanometers and 700 nanometers, kind of this violet light to red light. But you have this whole spectrum of electromagnetic radiation. You see some familiar things up there, X-rays, UV light, microwaves, radio waves, the whole 9 yards. So you say, light's part of the visible part of the electromagnetic spectrum. We often think of it 3 ways: rays, waves, and particles. So let me drop the knowledge. So ray optics is kind of the first model of light that we think of. It describes light as traveling in a straight line, rectilinear propagation. That's the fancy word for it. We all are familiar with this, right? You go out on a sunny day, you're casting a shadow, you hold your hand out, you see the shadow of your hand on the pavement, right? Looks like light travels in a straight line. This also is used to describe how we bend light, what we call refraction. Again, pretty basic. So you can take a lens or any material that's transparent and has a certain density, and you can shine light in it, and you can use that material to bend light. And so ray optics describes how that light travels in a straight line and can be bent by these optics or other objects. So it's useful for determining the properties of optical systems. And it uses this law called Snell's law to trace rays through a system. So this is Snell's law, how we bend light. So if you have an incident ray of light, this red arrow, incident on a surface, and the normal or the perpendicular to the surface denoted by that dashed line, and that you say you're going from air, this N1 up here, we call that the refractive index. That's just briefly the speed of light in a vacuum divided by the speed of light in the material. And so it enters this other material here, glass or water. And what's going to happen to that little ray? Well, according to Snell's law, which specifies the incident angle, the sine of it times the refractive index in the first media is equal to the refractive index in the second media times the sine of the angle there, you can rearrange it, solve for it, and see that that light ray bends. Pretty cool, right? And then we know just from experience that the angle of the ray that's reflected off of this interface is equal to the angle that's incident. And so that the key to this is really that change in refractive index. A simple way to think of it is perhaps maybe the density of the material is not quite right, but that's a good way to think of it. And that refractive index is dependent on the wavelength or the color of the light that's incident. So your patient says, okay, all right, that's cool, but I need something else. That's very heady. I need you to explain it to me in simple ways. Like, you know, if I was a spear fisherman in the tropics. All right, so imagine you're out there in the tropics, you're wading through some water and you got your spear and you want to spear one of these fish. So the real question is, when you're looking here, when you're looking down through the water, you see the fish right here, right? But the reality is, the light bends. So that fish is not here. This is a literal red herring. The fish is actually right here. And so when you go to spear that fish, if you try to spear where you see it, you're going to miss it. And so you actually have to adjust and compensate for the fact that light bends into that water. So ray tracing, it's very useful. It's used a lot in optical design. Basically, you can just apply Snell's law over and over again at each surface in an optical system, whether it be really complicated, like a microscope objective there, whether it's a reflective space-based telescope like you see here, or even our very own wonderful, beautiful eyeball. So you can describe, if you trace system like an optical system with all these rays, you can actually find there's 6 points that define an optical system. We call those the 6 cardinal points. They're outlined here for this single lens. Sorry, it's a little lower as an image, but briefly, they're the focal points, the front and rear, denoted by the capital F there. That's the point where if you were to shine light from really, really far away, the light would focus through that lens to that focal point. There's the nodal points, which are important. So if you shine a ray of light into this lens at a certain angle, it'll exit that lens at the same angle passing, assuming you aim it at the nodal point and it passes from the nodal point. And then there's the principal points, or principal planes, denoted by capital P there. And those are the planes basically where the light effectively bends through the lens. That's all very technical, but ray optics is very useful. But it doesn't completely describe light. So the second model of light we talk about is wave optics, and that thinks of light as a wave. So you get wave phenomena like constructive interference, where if you have 2 waves that are added together in sync, that you get a bigger wave. Destructive interference, if you add 2 waves that are out of sync by 180 degrees, they cancel each other out. And diffraction, which we'll find is actually useful in how we think about optics. And that's basically if you have light that is a plane wavefront and it shines through this aperture over here, instead of just propagating through as a plane wavefront, you actually get bending of light around the edges. And that's what we call diffraction. And that becomes important for us later as we talk about our pupil, where the light, as you try to localize the wave of light in that little aperture, it actually spreads out and you get these spherical waves. You all are familiar with this. If you've been to the beach or anywhere else, you see this breaker wall up here. You have plane waves from the ocean coming in, they're hitting this breaker wall. And what happens? They end up as these spherical waves emanating out. And so what's really interesting is if you took this breaker wall hole and you made it really big, the curvature would be less and less in these waves. They would actually become more and more planar, like the waves up there. But if you took that really small, if you made that hole in the breaker wall really small, then these waves would actually have more and more curvature. So the water would become more curved. And so water is a good way to think about wave optics because it's also a wave phenomena. So what's this diffraction have to do with vision? Well, imagine you got your eyeball here, right? Your pupil, your retina, and then you have a distant star way over there, a little point of light, right? So if you look at that little point of light, and you may notice this actually at night sometimes if you're looking at a small bright point of light somewhere far away, it doesn't necessarily exactly appear as a point. So you look at that little point of light, the rays from that point of light go into the pupil, and they focus on the retina. And you actually get this ringing pattern, and that's what we call diffraction. And that's because just like those water waves get bounced off of the edge of that breaker wall, light as a wave also gets bounced off the edge of the pupils. And so instead of having that nice little point exactly matched to a nice little point on your retina, it actually gets spread out a little bit. That's what we call an airy disk. It's diffraction. It's diffraction limited imaging. And we call that image of a distant star or a point object a point spread function. And what that means is if you image just a point with any optical system, you can describe how that point is translated into an image, and it's blurred out. Even if you didn't have any aberrations, if you didn't have any imperfections in your optical system, you would still get spreading of that point. So optical systems, including your eye, don't perfectly map the world as you see it onto your retina. So there is this question of, well, what's the optimal pupil size? Because if you had a perfect eye and you were only dealing with diffraction on one hand, you would want a really big pupil, right? Because as we think of that water analogy, if you make that pupil really big, the water is going to get the effect of the water ripples is going to be less. And so you can see this point spread function with 1 millimeter pupil is really big, but as you increase your pupil diameter to 7 millimeters, it becomes really small. So we all want really big pupils, right? No, wrong, because we have aberrations, and so we have imperfections in our optical system. And those usually scale with the diameter of the pupil. And so that as you go to a large pupil, guess what? The image of a star becomes more and more distorted as you go up and up and up. And so the optimal size of your pupil is really about 2 to 3 millimeters, right? That's where you have the tightest focus. And that makes sense because most of us walking around in daylight conditions have a pupil that's about 2 to 3 millimeters. And so your brain kind of optimizes that for optimal imaging. Diffraction isn't all bad. It can actually be helpful. How many of you here have heard of diffractive IOLs or intraocular lenses, right? You guys, probably a number of you have helped put them in eyes. And so they take advantage of the fact that light acts like a wave, and you can put these funny squiggly surfaces on the back of intraocular lenses and can use it to create a secondary focal point so that you can extend the depth of focus of an optic in the eye, and so that people can see not just at distance, but also a little bit up close. We call it a multifocal intraocular lens, and you can see a little bit how that works there. And then last but not least, the third model of light is quantum optics. So who here is ready for some math? I'm just kidding. We're not going to do that. Quantum optics really doesn't have a lot of use here. It's mostly, I hear some ahs. Thank you. I appreciate that. You're a good sport. So quantum optics is really a field that deals a lot with information, high energy physics, entanglement of photons, things like that. Doesn't have a lot of practical applications for us in the clinic, at least not yet, but it is a fascinating topic nonetheless. So your patient satisfied, you work him up and check his vision, and he's 20/40 uncorrected, but he pinholes the 20/20. He's back. It's like, wow, I didn't realize my vision was so bad. What makes my vision bad? Well, assuming the back of your eye is good, assuming there's no big problems in the back of the eye, it's probably due to your optical aberrations. What do I mean by optical aberrations? Well, we touched on earlier, optical aberrations really just mean there's imperfections in the eye or the imaging system that cause the light to be poorly focused instead of being tightly focused to that nice spot in the back of your retina. So why don't we see perfectly? You have these aberrations, and so if you take an image from a distant object like a star or something, and you make that point spread function, like I said, if you have a perfect eye, then all of those rays across the whole pupil in that upper eye model there will focus tightly to the back of the eye, and you'll get a nice tight point spread function. It's only limited by diffraction, no aberrations. But the reality is we all have imperfections in our optical system. Here in the lower eye, you have a example of spherical aberration. What spherical aberration simply means is that as you go out further into the pupil, the rays there are focused more tightly than they should be. And so you see those rays from the edge of the pupil end up focusing before the retina and blur out. And so you end up with this point spread function that's really massive. And so that can be the effect of aberration. There's like spherical aberration. So when we look at an optical system, when we look at these imperfections and the effect they have on imaging, we can describe them mathematically with these Zernike polynomials that many of you, and especially in the imaging department, are probably familiar with. When you get, do some of this imaging, you can return these Zernike polynomials. It's just a mathematical way of describing those imperfections in the optical system. They're described in the pupil plane, and the way to think about them is if you had a perfect wavefront that was going to focus to a perfect spot in that pupil plane, these are the deviations from it. And so you see this term here, the defocus term, is what we deal with mostly on a daily basis. That's responsible for myopia or hyperopia, meaning that the light is either focused behind the retina in hyperopia or in front of the retina in myopia. These other terms, astigmatism, that just means that the power of the eye in one meridian versus the other meridian is different. So you get different focal points depending on which way the light is entering the eye. That's also something we're familiar with. Both of those you can correct with glasses. And then the rest of these terms, all the rest of those terms, we just clump into irregular astigmatism. But but they do have effect on vision. And so you can see here, if you looked at the point spread function or that image of a distant star for each one of these terms individually, this is how that image of that distant star would look, depending on what aberrations you had in your eye. Here's a blown up view of this. And so you can see this point spread function here way over this image of a distant star. You know, it's really tightly localized. It's only limited by diffraction. But as you include spherical aberration, that sharpness goes way down. It becomes broader and wider. And so that point becomes more blurred. The same with coma. Only coma is not radially symmetric. And so you have some asymmetry in that spot. And that's when someone looks at a light source and they see kind of an ice cream cone shape up there, and the same with astigmatism. And so you can think of these wavefront aberrations as just additive. So if you had these different terms of Zernike polynomials in the pupil plane, you could add them together to get your total wavefront. That would give you this point spread function when you focus the rays through those aberrations. So instead of seeing a nice clear image, every point in that image is then blurred by your point spread function to give you this, what you actually see here. And so, so that's the way to think of these aberrations and these point spread functions, is they blur what you see by this point spread function. So how do you correct for it? Well, of course, like I already said, you know, these lower order aberrations, myopia, hyperopia, even astigmatism, you can correct just with glasses, contact lenses. Both of them you could correct with laser refractive surgery. But irregular astigmatism, really, you can't. You know, the control you have with glasses, contact lenses is not fine enough to really correct for these other high order aberrations. So that you'd have to turn to like something like laser refractive surgery. Okay, cool. So you refracted this guy. He pinholes down to 20/20, and he says, well, you put this black thing in front of my eye with a little pinhole. How on earth did that help me to see better? I don't understand it. It doesn't make any sense at all. Wouldn't that make me see worse? Well, now that you are armed with this knowledge, you can explain this, right? Why does a pinhole improve vision when you're checking vision? We already talked about how the most aberrated rays oftentimes go through the edge of the pupil. So if you mask the pupil down with this pinhole, you're cutting out all of those rays that are focusing not on the retina from the periphery. And so you see, you go from that image with the pinhole to here. So you cut out all of those worst rays and you can actually improve your vision quite a bit. And that's really how a pinhole works. So, okay, so you recompose yourself. You say, all right, well, let's see, you're seeing 20/40, but you pinhole down to 20/20. Let's see if we can refract you. I'll bet glasses will probably help you out. See if we can get you seeing a little better. So you start refracting him. He's like, I want more minus. He gobbles up that minus. How many of you got a patient like this? Right? They're like, give me the minus, especially when they're a young patient and they can accommodate well. And so you're giving a minus and they're accommodating right through it. And you're like, what is going on? He says, give me the minus. So how do you know if you've over minus the patient? You really don't, right? You don't unless you check. And one of the ways you can check, I don't know how many of you are familiar with the duochrome or the biochrome test. I don't know, is this something that you guys use? Yeah, a little bit, right? So this is a way you can check and see if a patient's been over minus. So basically what you do is you refract the patient, you whip out your duochrome, your cool duochrome glasses that are green and red. You whip out this fancy duochrome chart, which is green and red. So if you refracted them, you fog the eyes to about plus 75. And so at that point, the letters on the red side should be a little sharper for reasons that will be clear, no pun intended, in a second. And then you reduce that fogging by about quarter diopter steps until the letters on the red side and the green side are both equally clear. And if you did a good job refracting them and you didn't over minus, you should get back to roughly what your refraction was. Why? Well, this is the reason, right? Because when we talked about refractive index and Snell's law, we said that how light bends is also dependent on the wavelength of light, right? And that's true in your eye. So you actually bend red light a little less than you do green light. And so when you over minus someone, they tend to focus the green light on the retina, because that's what you're most sensitive to, right? That's what's the highest peak emission from the sun. And so you tend to focus that green light more sharply on the retina, and the red light's defocused. And so you see that green side pretty sharp, but the red side's blurry. So you add plus 75 to fog them, and that red side then becomes in focus because you've pulled back that red focus onto the retina. But now the green side's really defocused. So now what you do is you just decrease that fogging until the red light is slightly hyperopic and the green light slightly myopic. And what that looks like is that the red and green are then roughly equal clarity on the chart, or equal crispness. And that's how you know that you haven't over minus them. If you've over minus them, like I said, that green will be quite a bit sharper. Like I said, this works because refractive index is dependent on wavelength. And so this is, you know, if the red was sharp, you're at this upper situation where the red's tightly focused on the retina. If the green is sharp, you're at this lower situation where the green light's tightly focused on the retina. It's kind of complicated, but you can remember this mnemonic RAM gap, which means red add minus, green add positive. So you can just kind of algorithmically click through. So you get him refracted. He's pumped. He's like, wow, I'm seeing 20/20 with my new glasses. And then, you know, these patients, they always ask the questions that really matter for life. He says, do you think I should buy a sharp 120-inch 8K TV? It's got so many pixels, man. And you're like, all right. I haven't had my coffee yet. Okay. You look this TV up and you're like, what's he talking about? And you're like, oh my gosh. Are all those pixels worth it? It's only $10,525 a month for 12 months. How could you go wrong? This is clearly a solid life decision. I don't know about this. Deep breaths. Compose yourself. You got this. You have the power of optics on your side. So you're like, all right, let me ask you a question. You're seeing 20/20 now. Let me see what your setup is, what your bro pad. So he whips out a picture of his bachelor pad. You know, it's actually pretty nice, pretty clean. Got his couch, it's about 7 foot from his television screen. You're like, I don't know how he's going to get that thing up the elevator, but anyway, 7 foot away. So you think, well, he's seeing 20/20. What does that even mean anyways? What does Snellen acuity even mean? What does it mean to be 20/20 or 20/40 or 20/100? Well, 20/20 just means that, as you guys probably know, that if you're an emmetrope or you're seeing perfectly, then you can read the 20/20 at 20 feet, right? Whereas if you're 20/40, like this guy was before you refracted him, that means, you know, that someone who has perfect vision can see the 20/40 at 40 foot. But if you're 20/40, you have to walk all the way up, kind of the walk of shame, up to 20 feet to see the 20/40. And so you're in the situation here where if you got all your 20/20 friends way back there and you're 20/40, you got to be way up in front. How much does that suck? If you're 20/100, then your friends are even going to be way farther back. And so that's really what Snellen acuity means. And these letters on the Snellen acuity chart, they're not just any old letters. They're actually, someone thought hard about them, these what we call optotypes. And they actually have specific measurements and angular sizes. And so when you look at the 20/20 at 20 foot, it subtends about 5 arc minutes, whatever that means. So an arc minute is 1/60th of a degree of arc. Now, for reference, everybody's roughly symmetric. He's human. So if you hold your pinky out up like this at an arm's length and you close one eye and you look at your pinky, the width of your pinky is about 1 degree of arc. So you got about 360 pinkies all the way around you. Now, what you can do is when you see the moon all big and big and whatever in the sky, right, when it's coming up, the moon is always about 1/2 degree of arc. So if you close your eye and hold your pinky up, that moon will go down to 1/2 the width of your pinky all the time, whether it's on the horizon or up in the sky. Same with the sun. I don't recommend looking at the sun. Okay. So anyway, so this E on the 20/20 line subtends about 5 arc minutes. And the reason is because the humans can resolve generally 1 arc minute. And so each arm of this E is 1 arc minute. And so it subtends 5 because you can then resolve each arm of the E. All right, that makes sense. And so this is really clever design of this chart. So, okay, so you know when he's best corrected, he sees 20/20. So he can resolve, you know, 1 arc minute. You pull open the specs for this big, huge TV and you see what the deal is. It's 120 inches. Well, as you know, TVs are measured along the diagonal. So you got to figure out what the horizontal and vertical width is. You look at the number of pixels. Gosh, that's a lot of pixels. and it's 8K, man. Whew. And then you dig way down into the manufacturer specifications and you find this magical number. It's called the pixel pitch or the dot pitch. And what that number means is that's the spacing between each pixel, right? So if you had your CCD array or your screen here and you looked at the distance between these adjacent pixels, that's what the pixel pitch would be. And they list this as 0.3 millimeters. Disclaimer, I did check their math and I don't know if I quite agree with them, but we'll let it be 0.3 millimeters, okay? So the patient's 20/20, you can resolve 1 arc minute. How are you gonna solve this problem? You're gonna whip out some optics. So 7-foot viewing distance, 20/20 vision. If we look at our model eye and our detector and we use our nodal point, oh man, coming back from the beginning of the lecture, it's the comeback king. So the nodal point, remember, if you have an angle coming in, it comes out at that same angle. So he can resolve 1 arc minute. You know, you can resolve 1 arc minute here. You have the dimensions of the eye. You have the distance from his eye to his TV. You can use some geometry, some similar triangles, however you want to solve it. And you can then solve for what the minimum size of a pixel he can resolve at 7 feet. That's really what you're solving for here. And you find out that at 20/20 vision at 7 feet, the smallest object, the smallest thing you can resolve if you have perfect vision is about 620 microns or about 0.62 millimeters. How's that compared to the pixel pitch? It's bigger. It's bigger. So are the pixel, is that TV worth it? Is it worth it? No, it's a waste of money. And so at 8 o'clock in the morning, before you even had your coffee, you have saved this guy $126,000. Good job. So this guy would need to sit 3.5 feet from his TV to actually have his visual acuity well matched to the pixel size. You know how close 3.5 foot is to a 120-inch TV? That's pretty close. So in other words, you really only need half the number of pixels for the screen size at 7 foot. So you don't have to spring for the 8K, you can spring for the 4K. Wah, wah, wah. Maybe it has less street cred, I don't know. So you answer that question, you're like, oh my goodness, we love our patients, but I think I see the doctor coming. So I'm gonna just step out. Have a nice day. So your patient, thank you. It's very appreciative.